In this video, we'll do a quick review of the properties of logarithmic functions. Before we start talking about the rules of logarithmic functions, I just wanted to refresh your memory on what a logarithm was. We know that if we have something that says log base a of x equals y, that is equivalent to a to the y equals x. So for example, if we see something that says log base 4 of 16, we're saying, what is the exponent that you need on 4 to get 16? And of course, the answer is 2. If we were to write it in the exponential form, it would be 4 squared equals 16. So basically, a logarithm is an exponent. So we only have 3 rules for logarithmic functions, the first being the product rule. It says if you have the log of a product, log base a of m times n, you can write it as the sum of log base a of m plus log base a of n. So taking a look at this first example, we notice there is no base here. Remember, that means it's the base 10, the common log. We can break this up as log 9 plus log 27. For the next example, we can do the same thing, only this time we have base 3. So log base 3 of 9 plus log base 3 of 40. Now, in this particular case, we can simplify this because we know the power we have to raise 3 to get 9 is 2. So 2 plus log base 3 of 40. For a natural log, it works exactly the same. The base is e. This would be the natural log of 12 plus the natural log of 53. And similarly, we can do this with variables. Log base t of 8 plus log base t of y. So that's the first rule. The second rule is the quotient rule. The quotient rule states if you have the log of a quotient, you can separate it as the difference of the logs. Log base a of m divided by n is equal to the log base a of m minus the log base a of n. So in a similar way, we can simplify. In this particular case, we'd have log base 2 of 6 minus log base 2 of 48. If you want to, you can think of this fraction bar here as this negative. For the next one, we have log base 2 of 16 minus log base 2 of 90. And again, on this one, we happen to know that 16 is a power of 2, so we could simplify that as 4 minus log base 2 of 90. And we may also be able to separate this further, but just for the process of refreshing our memory, we're going to stop there. This works for variables only, or also, we can make this log base 5 of x plus 1 minus log base 5 of x minus 2. Our third and final rule is the power rule, which says if you have the log base a of something to a power, you can bring that power down in front of the logarithm. So for this example, if we have log base 3 of 5 to the 8, we could bring that 8 down and make it 8 times the log base 3 of 5. To be honest, this power rule is probably one of the most powerful tools, something like the zero product rule that helps us solve lots of equations. For this next example, we'll bring the 2 down to log base 3 of x. And for the last one, and we have to be really careful here, I put parentheses here, but oftentimes it might just look like log base 4 of 5 to the x minus 2. when you bring that x minus 2 down in front, it's really, really important that you put those parentheses, because if you don't put those parentheses, you can see it would just look like x minus 2 log base 4 of 5, and we really want to multiply that entire exponent by the log base 4 of 5. So here's a summary of those properties. They are listed here, but notice I have a couple of others. I have also the change of base formula. Many of you will have on your calculator, when you go to math, you'll have a key that says log base, which means that you can take something that is log base 3 of 7 and actually type it in the way that it looks. But if you couldn't do that, if your calculator doesn't have that, you would write it as log 7 over log 3. And you could make this any base you wanted. We typically would make it either base 10, I'll slip that in there, or you might make it the natural log, only because those two we can use our calculator with. This is also helpful when we're solving algebraic equations. You may need to use the change of base formula so that you can write everything using the same base in order to proceed. The other properties are not really other properties. They're just special cases of the original 3. So let's talk about those super quick. If you have log base 3 of 3, for example, this first one, it's asking us what power do you have to raise 3 to get 3? And of course, that's 1. So as long as these two values here match, your result will be 1. Similarly, if you have the log base 4 of 1, for example, this second rule, what power do you have to raise 4 to get 1? That result is 0. So again, if you have log base a of 1, regardless of what the base is, your result will be 0. Taking a look at this one, we say, what power do you have to raise a to get a to the x? And that's x. That should be pretty straightforward. Now this one's a little bit harder to wrap your head around. I suggest that you just memorize it. But basically, think of this. If you have a to the log base a of 7, for example, this is currently in exponential form. So I'm going to say equals question mark. If I convert it to logarithmic form, that would be log base a of question mark equals log base a of 7. Therefore, that would need to be 7. So if you had a to the log, let's just change that. Let's make that log base 5 of 4. So we're going to have 5 to the log base 5 of 4. That would be 4. There are a couple of common errors. I'll let you read through those. But make sure that you do, because very often people try to make up their own rules. Remember, there are only these 3. Okay, let's take a look at some examples. Evaluate the following using the change of base formula. Write it both as a common log and as a natural log. So for this one, we would have log 8 over log 4, or the natural log of 8 over the natural log of 4. In calculus, we often need to expand, in other words, express a logarithmic expression as a sum or difference of logarithms. So in this particular case, the first one, we're going to use our power rule, and that's going to give us 2 times the log base 4 of x plus 1. So you'll notice on the previous page, one of the common errors is that people will take a log base 4 for something like this, and they'll try to distribute that log base 4. We would never do that because log with a base of 4 by itself isn't anything. You have to have an argument here. So it doesn't make any sense to take this as its own entity and distribute. For this one, this is another one that has common errors. Notice that the 2, the square, is only on the y. So what we would need to do here is break this up first as a product, log base a of x plus log base a of y squared. And then that 2 will only go in front of the second log, 2 log base a of y. So we couldn't move that 2 initially because it's only on the y. Had it looked like this, log base a of x times y squared, and the 2 applied to both, then we could. Here's another one that includes all of our rules. So what we have here, we have a division, we have multiplication in here, and we have powers. So the first thing I'm going to do is rewrite this as log base 4 of x, y, z cubed, that's the numerator, minus the log base 4 of w. Now I could write the square root of w, but I'm going to write it as w to the 1/2 because I don't have any rules for square roots. I only have rules for exponents. I'm now going to separate this one as a product. So log base 4 of x plus log base 4 of y plus log base 4 of z cubed minus log base 4 of w to the 1/2. And then as a final step, I'll take these exponents and move them down in front of their respective logs. So that's going to give us log base 4 of x plus log base 4 of y plus 3 log base 4 of z minus 1/2 log base 4 of w. So I have a few more examples here to cover with expanding. So again, on this one, you'll notice I have a multiplication and I have a multiplication here in my denominator. So I'm going to start with my quotient rule and say log base b of 3x squared minus log base b of w to the 5th, y to the 4th. At this point, I'm now going to use my product rule. Now we have to be careful here because we're really subtracting this log. So when I do that, I'm going to need to add some parentheses here. So this is going to be log base b of 3 plus the log base b of x squared minus, and I need those parentheses because I'm subtracting that log base b of w to the 5th plus log base b of y to the 4th. And you can see I'm going to do two things on this last step. I'm going to move these exponents down to their respective logs, but I'm also going to distribute this negative sign. So our final result will be log base b of 3 plus 2 log base b of x minus 5 log base b of w minus 4 log base b of y. So notice, and this is important, the two things that have the minus sign in front of them, they came from the denominator. And that's going to help us when we have to condense these logarithms back. Another note as I was doing this, how we say this is important. We say log base a of x. So log, we say base a of x. I often hear log a of x, log a times x, log a to the x. but all of those are incorrect. We want to make sure when we write it that the base is actually a little bit below the logarithm, and if we happen to have an exponent, we want to make sure that that's actually above. If you're somewhat lazy and you write this, it's going to look like log base 10 of ax, and you're not going to know necessarily that your a is the base. Okay, let's finish this up. I have one additional example that's more algebraic. So this one is something you might see in calculus. Notice that there's a little more, it's a little bit more involved, but the rules are the same. So we're going to start with our quotient. So this is the natural log of x plus 2 cubed times x minus 4 to the 5th. That's the log of the numerator minus the log of x squared times x minus 2. So we have the log of the numerator minus the log of the denominator. At this point, we will use the product rule for both of these, and we will have the natural log of x plus 2 cubed plus the natural log of x minus 4 to the 5th minus, don't forget your parentheses, the natural log of x squared plus the natural log of x minus 2. As a final step, we'll bring our exponents down in front of our respective logs, and we will also distribute this negative sign. So we're going to have as a final result the natural log, 3 times the natural log of x plus 2 plus 5 times the natural log of x minus 4 minus 2 times the natural log of x minus the natural log of x minus 2. So we should be able to take a logarithmic expression and expand it. But sometimes, especially when we're solving logarithmic equations, we also need to condense them. And again, I'll call your attention to the fact that when we have things in the denominator, those things appear in the expansion with a minus sign in front. So when we look at this first example and we want to condense them as a single logarithm, keep that in mind, you should only have one log, and this one is base 10, anything with a minus sign in front of it, like the log 4 and the log 6, should come from the denominator. So that will be 4 times 6. And the top ones, which have plus signs in front of them, those will come from the numerator, 3 times 5. So we'll end up with the log of 15 over 24. We could simplify that. 15 is divisible by 3, and 24 is divisible by 3, so we could write it as log of 5/8. Let's do the same thing here. This is plus, so we don't have any division. Single log would be the log of 2x cubed times 3x squared, and then simplifying this, we'll have the log of 6x to the 5th. A little bit more polynomials in here. Same rules. I have a log minus a log. That must have been a division. The thing with the minus sign is in the denominator. So we have 3x minus 1 over 3x squared plus 5x minus 2. Here's another one. 2 log x. Well, remember when we were expanding, the last thing that we did was bring the exponents down. So now the first thing we're going to do is move these exponents back up. So we will have log of x squared plus the log of x plus 1 cubed. And since this is a plus sign, we can condense it as a single logarithm with a multiplication. So just a few additional examples. We should be able to simplify some things without a calculator. We talked about this rule earlier. Log base a of a to the 7th says, what power do you have to raise a to get a to the 7th? That should be 7. A natural log, of course, is base e. So we don't write it that way, but we could write log base e of e, in which case, what power do you have to raise e to get e? That's 1. And then the third one, as long as the base 7 and the log base 7 are the same, we say 7 to the log base 7 of 4 is that number that doesn't match, 4. One last example here. You will see these in your homework. Given that log base 10 of 2 is 0.3010 and log base 3 is 0.4771, find the following if possible. So both of these are base 10. We don't write it. And all of the examples here are base 10. So if I only know log 2 and log 3, then I would need to write 18 using 2's and 3's only. So in this case, I could do 2 times 9, and of course 9 is 3 times 3. So I could make this log 2 plus log 3 plus log 3, and then I would use these values. So 0.3010, 0.4771, and 0.4771. I get 1.2552. We can check that on our calculator, log 18, and we get 1.25527 and so on, but we only had 4 decimal places here. Okay, let's look at the next one. Well, the next one, I could bring this 2 down in front. So 2 log 9. Well, I don't have 9, so maybe I write 9 as either 3 times 3, like I did previously, or I could write it as 3 squared, in which case I can bring that 2 down in front again and get 4 log 3, or 4 times 0.4771. That gives me 1.9084. Lastly, we have here log 12. I have to write this in terms of 2's and 3's. So I could write this as log 2 times 6, or since 6 is not one of the numbers I know, I could write the 6 as 2 times 3. Alternately, I could have written it as log 2 squared, which is 4 times 3. Either way will work. So for this one, it's log 2 plus log 2 plus log 3. And then using the numbers above, we get 1.0791. If I do it this way, I would write this as 2 log 2 plus log 3, and I would get the same result. That concludes this review of the properties of logarithms. Thank you.